Section 8.2, Properties of Exponential Functions. Here we have families of exponential functions. We've seen this in the past with other parent functions. And what we have is when I add or subtract or multiply constants to my function, that function changes. And that is similar to our parent function of exponential functions. Here, my parent function is y equals b to the x. And when I have y equals a times b to the x, my function will change. It is called a stretch when my a, the absolute value of a, is greater than 1. In other words, my function will increase more rapidly or stretch my y-axis quicker than it would just be my b to the x. My a, if it is the absolute value between 0 and 1, my function will still increase, but I will need to go out further on my x-axis for that to increase. My stretch increases my y-axis or values quicker than my shrink. A reflection. A reflection is when a is less than 0. That will take each point on my original function, or my parent function, and reflect it over my x-axis. Translation. This is going to be horizontal by h and vertical by k. And what we see here is b to the x minus h. If I have x minus h, then my function will transition to the right. If I have x plus h, my function transitions or moves to the left. We've seen that on other functions. If I have a plus k, then my function will transition up or move up. If I have a minus k, my function will transition down or move down. And these move the same number of constants of h and k. And I also can have a combined function of y equals a, b, x minus h plus k. Let's take a look at some of these translations. Here I have my parent function of 2 to the x. When I graph this, I have a function with its ordered pairs. I plug in 0, I get 1, 1, I get 2, 2 to the second power is 4, 2 to the third is 8, 2 to the negative 1, remember that's the reciprocal of that, which is a half, negative 2, again reciprocal, and I get 1/2 squared, which is the fourth. And I plot this function. And as in the past, we've labeled our asymptote. In other words, this is the place where my function will not intersect. And here, it will not intersect at y equals 0. I know my domain, or my x values are x is any real value, and my range, which are my y values, and my y is greater than 0. Now, if I start with my parent function of y equals 2x, or any one that you want to start with, y equals 3x, y equals 4x, then we can show transitions or translations off of this. So let's take a look at a function that is changed by just adding my h. So this is 2 to the x plus h. What I've first done is I've graphed my y equals 2 to the x. That was on my previous slide. Now what I've done is I have x to the h. Well, recall when I have x plus h, I transition that to the left, or translate it to the left, that many units. So I'm going to move each point 3 units. And as I do that, notice in my original graph I would have 2, 8. Now I move that to the left 3 units, and I would have 0, 8. But it's easier just to graph my y equals 2 to the x. So graph your parent function first, and then proceed to translate how the problem is given to you. Here my translation is to move each point 3 units left. So it's easily to graph my y equals 2x, and then move 3 units left on each one of my parent function points. And when I do, I end up with this given graph in the blue. This is y equals 2 to the x plus 3. Again, I can find my domain where x can be all real numbers, and my range, y, where y is greater than 0. And my asymptote is still going to be y equals 0. And as stated, horizontal translation does not change the asymptote of my parent function. And notice all this did is move my parent function to the left 3 units, or the number of units given in my problem. On my next example, I have y equals 2x minus 7. I first graphed my parent function of y equals 2 to the x. Now I take a look at the translation to the parent function, which is a minus k. And recall from our previous slides, a minus k means I'm going to translate my function down that many units. So all I did is graph my parent function of y equals 2x, and then take each ordered pair and count 1, 2, 3, 4, 5, 6, 7. I did that on each successive ordered pair. 1, 2, 3, 4, 5, 6, 7, until I've completed my graph. Now, what that did is give me this graph from my original parent function. So the graph here in blue is y equals 2 to the x minus 7. And now I can find the domain x such that x is all real numbers again. My range y such that y here is greater than my translation, which is a negative 7. From my range, I can see that my asymptote for my new function y to the 2x minus 7 is y is equal to a negative 7. My new function will not intersect this horizontal line at y equals negative 7, where its asymptote. Notice the original asymptote was at y equals 0, but it moved down 7 units. Next, again, I graphed my original parent function. Here it is still y equals 2 to the x. And now I have y equals a negative 2 to the x. What this really is does not mean that the negative 2 is inside of parentheses with the exponent. This is really y equals a negative 1, and then this is 2 to the x. In other words, I substitute in for my values for x, I get a value, and I multiply that by a negative 1, which takes every ordered pair from my original parent function and just multiplies it by a negative 1. Therefore, when I substitute values in for my x, such as 3, I have 3 to the 8 on my original function. I have 3 to the 8 again, but I multiply by a negative 1. I get 3 to the negative 8. And I do that with each successive ordered pair until I achieve my new function, which is y equals a negative 2 to the x, which, as you can see, is a reflection of each ordered pair from my parent function over the x-axis. My domain, x such that x is still all real numbers, and my range, y such that y is less than 0. So here, my asymptote for my original function is y is equal to 0, still holds true for my new function. My function still will not intersect my x-axis, which is y equal to 0. So even though my function has flipped over the x-axis, my asymptote is still the same for each of these two functions in this situation. In this example, I have a stretch because my value for a is an absolute value of a here greater than 1. Therefore, that is a stretch. Now, how we achieve that is, again, I graph my parent function of y equals 2 to the x, which I know how to do very easily. Remember, I have 0, 1. I have a negative 1.5, a negative 2, which is a fourth, 1 that is 2, 2 is 4, and 3 is 8. Now, all I do is take those same values. For example, 0, when I substitute 0 into my original function, I get 1. But now I take that 1 and multiply it by 3, so I have 0, 3. 1, when I substitute in, I get 2. 2 times 3 now becomes 1, 2, 3, 4, 5, 6. For negative 1, I have a 2 to the negative 1, which would be a half. but a half times 3 is 3 halves, or 1.5, which is here. If I substitute in a negative 2, I get a 1/4, which gives me 1/4 times 3, or 3/4. And you can see this is a stretch because it stretches my y values from my original function. It goes up a lot quicker. So this is y equals 3 to the 2x. I can find my domain. My x values are still all real numbers. My range, my y values, are y greater than 0. And my asymptote has not changed. It is still y equals 0. The previous slide was a stretch. This, my a is between 0 and 1, the absolute value of it is, and that is a shrink. As you can see, my original function, the black, is y is 2 to the x. Then all I did is take that ordered pair of y value and multiply it times a half to achieve my new function with a shrink. So if I started at 0, 1, 1 was the outcome when I plugged in 0, and I get 1 times a half, so I get 0/2. 1, 2 to the first is 2, but 2 times a half is 1. 2, when I plug in 2, I get 4, but 4 times a half, I get 2. And that is continued where every ordered pair occurs from my original parent function. And you can see what happens is this is a shrink. In other words, my y values do not increase as rapidly. And I can find my domain. My x values, x continues to be all real numbers in this situation. And my range, my y values, are still y greater than 0. As on the previous slide, my asymptote stays the same, y equals 0. Both of these functions will not intersect at y equals 0. On my next example, I want to graph y equals a negative 4, 2 to the x minus 1 minus 1. From viewing this, I know that I'm going to have a growth. I have a transition to the right by 1. I have a stretch by 4. And I have a vertical translation down 1. To perform this operation, I first graph my parent function, which is y to the 2x. And I create the table of y to the 2x. And you can see I have graphed that function. Now what I'm going to do is start at each point. I'm going to start at a negative 3. I'm going to move my point to the right 1, multiply the value of y given in the table by a negative 4, and then place the point and then do a vertical translation down by 1. So let's begin. Start at a negative 3, move it to the right 1, multiply the value of negative 3, which is 1/8, by a negative 4, and 1/8 times a negative 4 is a negative half, and then move that value down 1. And then we're going to continue that process. I start at a negative 2, horizontal translation to the right 1. The value of 2 is going to be 1/4. 1/4 times a negative 4 is a negative 1, and then a vertical translation down. Let's go to the next point, which is going to be a negative 1. My negative 1 goes to the right 1. A negative 1 is a half. A half times a negative 4 is going to be a negative 2, and then a vertical translation down 1. Now I'm going to go to 0. 0 moves to the right 1. 0 has a value of 1. Multiply by a negative 4, I get a negative 4 with a vertical translation down 1. And I'm not going to do my 2 because it's going to get too small on the graph, and I can't graph that there. So I'm going to go with 1, move to the right 1. 1 has a value of 2. 2 times a negative 4 is a negative 8 with a vertical translation down 1. Now you can see I have plotted my new function using translations from my parent function. And if you can see, each ordered pair is moved to the right and then translated down by the value of a stretch of 4. Now I need to determine my domain. My domain, x such that x equals all real numbers. My range, y, such that y has to be less than a negative 1. And that sets up my asymptote at a negative 1. So you can see I have a vertical translation down, a horizontal translation right, and a reflection with the minus sign, so you can see it's reflected, and a stretch of 4. My next example, I want to graph y equals negative 12, 1/2 bx. Here, since b is between 0 and 1, I know that it's going to be a decay. I know that I have a reflection over the x-axis by the negative, a stretch of 12. The first thing I want to do is plot my parent function, which is y b to the x. Here, b is a half, so I want to plot y 1/2 b to the x. I've already found the values of that in my table, and I plotted the parent function. Now all I want to do is translate the ordered pairs in my parent function by the negative 12, which is the only stretch in my problem with the reflection. So here I'm going to translate, starting with the point 0, 1. So at the x coordinate of 0, I have a 1, but I'm going to multiply that by a negative 12, which is not on my graph, so I'm going to guess that it's about here. Next, 1 plots at a half. So 1 is at a half, but a half times a negative 12 is a negative 6. Next, I have 2 as at a fourth. 2 multiplied by negative 12 times a fourth is a negative 3. Next, I have a negative 1 plotted at 2 with a value of 2, negative 1 at 2. 2 times a negative 12 is a negative 24. So you can see that's really going to drop down here and just go farther. And my plot for a negative 2, 4 is going to be at a negative 48. So you can see this is going to be my graph. What I really need to determine is how close this gets to my x-axis. So maybe I'll choose a value out here somewhere to see how close it gets. So let's plot a value of, let's say, x and a y, and let's do our parent function, and let's try x being 6, 1/2 to the 6th power, and I'm going to have a fraction of 1 over, and this is going to be 2 times 2 is 4 times 2 is 8, times 2 is 16, times 2 is 32, and times 2 is 64. So this is going to be 1/64. So that's going to plot at 6, 1/64, which is very close to the x-axis. Now what I want to do is multiply that by a negative 12. And of course we know that a negative 12 times 1/64 is negative 3/16. Then I can plot my function. And I wanted to determine this point because I wanted to see the asymptote, which is y equals 0 for actually both functions in this case. Determine the domain. X, of course, x equals all real numbers. And my range, where y is less than 0.